In this presentation, I will walk you through how to apply a random forest model within the context of an analysis project. Um, let's start with the external example for a random forest in Python. To begin, I reference an external tutorial that demonstrates how to implement a random forest in Python using a different dataset than the one used in my project. The tutorial can be found in the following QR code. This example uses the well-known bank marketing dataset derived for a series of telemarketing campaigns performed by a Portuguese banking institution. The general context of our example is that the dataset contains various socioeconomic and customer-related variables such as age, credit default status, consumer price index, consumer confidence index, and the target variable y, which indicates whether the customer subscribed to a term deposit. The objective is to predict whether a client will subscribe using a random forest classifier. So, what is the process for this example? The tutorial follows the complete machine learning pipeline, importing the libraries first. This includes pandas, numpy, matplotlib, and skitlearn. Then, we are performing the minimal preprocessing, such as mapping yes or no, responses to binary values. Then we're splitting the dataset into training and test partitions. For the fourth step, we are feeding a random forest classifier using default hyperparameters. And then we need to evaluate the model accuracy. Here is the model accuracy. And finally, we visualize the structure of a few individual trees. This example is valuable because it illustrates a clear, practical implementation of random forest, and it provides a methodological reference for the modeling approach that now we are going to apply to our own project. So our project is named Dynamic Supply Chain Logistics. This is a project overview. Our work focus on dynamic supply chain logistics uses a real-world dataset derived from a logistics network operating in Southern California from 2021 through 2024. The dataset description is that the dataset contains 32,066 operational records with 26 different variables describing the behavior of logistic routes. The variables capture a wide range of operational aspects such as loading and unloading times, the traffic congestion levels, the customer clearance delays, weather severity, route complexity, ETA variation, and fuel consumption rates. However, what is the problem for this dataset? What is the problem statement? Although modern logistic networks generate large volumes of real-time data as we just see in the dataset, organizations often find it challenging to convert this information into reliable predictions, early warning signals, risk classifications, and informed decision-making tools. So our goal of this project is to use the data-driven methods to classify the road risk levels and extract actionable insights. Let's remember that the road risk level is going to be divided into moderate, high, and low level of risk level. So to accomplish this, we're going to apply three different analytic techniques that we use throughout the semester. The first one is clustering, the second one is decision trees, and the third one is random forest. Regarding the clustering results, the first method applied in the project is k-means clustering to visualize the clusters into a two-dimensional space. So we are going to use the principal component analysis, the PCA graph, which is used to project the higher dimensional dataset onto the two principal components that capture the most variance. So which ones are the observations from the PCI clustering output? The algorithm identifies 4 meaningful clusters within the 32,000 routes. While some overlap is present due to the PCA dimensional reduction, distinct patterns still emerge. As we can see, we are using 4 clusters, and the cluster centers represent a red star, fall directly at the densest areas of the respective groups. All of this indicates that the routes in this logistics network naturally from 4 behavioral groups, each represents different operational characteristics. These clusters provide a useful segmentation foundation that informs the next stage of risk classification. Now let's move on with the decision tree results. For the project, we implemented a decision tree model to classify the road risk. This model is more advantageous because it generates interpretable, rule-based structures that can be easily communicated to operational managers. Since a decision trees function just as well as how the mind processes information in order to make decision making. So what are the key findings from the decision tree that we just performed? Is that traffic congestion is the most influential predictor of route risk. Low congestion generally corresponds to low or moderate risk levels, where high congestion increases the likelihood of elevated risk, depending on other conditions. For the ATA variation, this is a strong indicator of high risk. Routes that combine congestion with significant ETA variation consistently lead to high-risk terminal nodes. These leaps contain large sample counts indicating consistent patterns. Then, we saw that we have a stable operating conditions mapped to low-risk outcomes. Low congestion and mild weather and efficient handling times typically produce low-risk predictions. For the operational delays produce more moderate risk. Customs delay, long loading times, and warehouse processing issues often result in moderate risk levels, situations that are not severe but still operate unstable. For the leaf sample size that validate the model, many end nodes contain hundreds of samples, highlighting broad, generalizable relationships rather than isolated anomalies. In this part, we change the decision tree from the past presentation because our node that had an entropy of 0,0 only had 3 samples that were not representative out of the 32,000 samples that we have in the dataset. Because of this, we redid the model, and now we have this more containers of nodes of hundreds of samples. But while the decision trees provides useful transparency, it can be sensitive to noise and tends to overfit. For this research, a more robust ensemble method, such as the random forest, was applied as the final step. Let's remember that the final random forest is like a conjunction of several decision trees. In this way, it's more precise and less biased. So now we're going to do the random forest implementation. A random forest classifier was constructed to enhance predictive performance and generate a more comprehensible ranking of variable importance. And finally, the structure of several individual trees was visualized, both horizontally and vertically. But why a random forest? A random forest improves upon single decision trees by reducing the variance, mitigating overlifting, improving generalization, and capturing nonlinear relationships. They achieve this by constructing multiple trees on random subsets of both data and features, and then aggregating their predictions. But with these results, now we have more insights for our project. So what were the insights from the random forest? The random forest provides a deeper, more reliable assessment of which variables drive logistic route risk. The top predictions that were identified was the loading and unloading time. This emerged as the most significant variable. Long handling times often correspond to operational bottlenecks and correlate strongly with high risk. Then the customer clearance times. These delays in custom processing increase uncertainty and contribute significantly to high-risk predictions, as well as the traffic congestion levels, confirming the decision tree's results. Congestion remains a key determination of risk. Another factor is fuel consumption rate, which higher or irregular fuel consumption suggests route inefficiency or suboptimal driving patterns. Now, for the weather severity, adverse weather conditions tend to shift risk classifications from low toward moderate or high risk, depending on the weather. Now, comparing the random forest to the decision tree, the random forest model provides several additional advantages, such as the higher predictive accuracy due to the ensemble effect, greater robustness against noise or outliers, and a precise variable importance ranking, which quantifies contribution rather than relying on the decision tree structure all alone. The ability to identify subtle interactions between variables that may not appear in a single tree, this is a very important factor for using a random forest. So over and the random forest depends understanding and increases reliability, while the decision tree offers a clear set of interpretable results. So for the operational implication and final insights, by interpreting results from the cross-setting analysis, the decision tree, and the random forest, several practical insights emerge from a supply chain operation. The first instance is low handling times are the clearest indicator of high risk. This emphasizes the importance of improving loading and unloading processes to reduce downstream disruptions. Then, routes with low fuel consumption, quick handling, and mild weather consistently fall into low risk categories. These represent ideal operation conditions. Then, regarding congestion, customer delays, and ETA availability collectively indicate high risk scenarios. These factors should be monitored closely to trigger proactive mitigation strategies. The decision tree provides understandable rule-based classifications, while the random forest provides more robust and accurate predictions, we are saying. Together, they give a comprehensive analytic framework capable of supporting real-time decision-making and risk assessment. So in conclusion, we began by reviewing an external example of a random forest applied to the bank marketing dataset. Then, by introducing the supply chain logistic, we described the dataset and the operational context. Then, we presented the clustering results so we can understand the behavior of different groups. In this case, it was 4 clusters. Then we can say that the combination of these different techniques demonstrate the effectiveness of machine learning approaches in transforming large-scale operation data into actionable insights that can significantly improve logistics planning and risk management. Thank you for your attention.